Yeah. Well, we're back.
It knew we were.
Sorry about that, everyone. The computer crashed.
I'll get back to this thing.
Yeah.
Okay, welcome back. Okay, so we were talking about the different ways we could do it. It could be literally in the same JavaScript process. If you were writing your game in C++, you might be using the Klingo C++ API. Then you would have a similar question of does it run in like a child process or not. This is just sort of the web version of that. But finally, you might think like this download up front is still really annoying for our mobile users. And on top of that, maybe people in a desktop browser, the JavaScript version of the answer set solver responds fast enough, but depending on which generation of phone you have, that whether it has an optimizing JavaScript JIT, doing combinatorial search in JavaScript on your cell phone may not be the right solution. So you might next think, well, let's take this native Klingo binary executable and run it in the cloud. The native solver is very fast. We get our solutions in a quarter of a second. The downside is now that we depend on the entire internet working and our path to it, the local Wi-Fi, Google Cloud Services being up. In order to debug this system, you need to be aware of a whole lot more than just serving up static web pages. So it has some downsides. One of the big potential downsides is that all these people are now solving their combinatorial search problems on one central place that we have to pay for, rather than on their own device. But page remains responsive, and there's no upfront download. It's just a very lightweight page. So none of these things is perfect, but we're going to go with a variation on the one on the right. In particular, we built on top of the Google Cloud Platform tools. So we have our game here. We have the answer set solver, Klingo, down here, running in some server somewhere out there. But instead of just having one of these talk to the other one directly, we want to make it so that if you lay down some evidence and pick it up and lay down something else, like if you're repeating a state you were just in, you shouldn't have to talk to the server to get the identical problem solved. We can answer a bunch of these sort of backtracking and try something different type requests out of a local cache. Likewise, if several people in the same geographic region are solving the same puzzle of the day and everyone wants hints for the opening frame of the New York Times puzzle of the day, we probably have that answer in our global cache. And then finally, if you're the first person that gets to a state that is in our cache, it finally talks to the answer set solving service. But each of these things are set up in a way that there's no single point of failure. It auto scales as needed. So I imagine if you had zillions of players, we're not going to have trouble with our site going down. We'll have trouble with, wow, we didn't do as much playtesting as we thought, and there's other types of bugs going on. So as like some of the great things, all these duplicates, we avoid actually running the answer set solver a lot. We're building on top of very good infrastructure here. We have no support for offline play because everyone must be, for every interaction, live on the internet. I guess we could have been clever and had local solving in case you were offline, but you would still have to download the solver in that case. Not perfect. And one of the things about building on this infrastructure is that you do pay per CPU second, but only after you exceed certain limits. And we budgeted that we could, with 1 million puzzles with a typical number of button presses and so on, handle about 1 million puzzles per month without paying anything, just staying within the free tier. So this is meeting our sustainable goals, like there can be a spike of popularity and it handles the load. People can ignore the site for 2 years and it hasn't cost us anything, except for $10 a year for the domain name or something like that. So it's not the ideal solution, but we got a lot of things we like out of it. And the experience of building this has already informed some of the other ASP-based tools we're making in the lab, where we want to deploy a service for analyzing Twine games. Oh, we'll use a similar caching architecture. We'll use the same backend service. One note I'll make about software licensing. For many years, Klingo was licensed under the GPL license, which was great for, well, I don't know, it was for the intent of the project creators. They've switched to the MIT license. This is significant from my experience because I know from being at Microsoft and in a few other industrial contexts where like, you did some really cool stuff with ASP, but we basically cannot touch it in our code because it needs to be licensed in a different way. Now, if you include the right notes in your about box, you can build on this stuff in a commercial setting. One last brief note on the computational complexity of some of these things. Many of you, or some of you, have maybe written a Sudoku solver in like a AI class project. It's easy enough to solve Sudoku boards, and when people import their own puzzles, we run a quick solve to find out if it has a unique solution or not. Likewise, if somebody gives you a set of evidence and the rest of the board, checking if there is a solution that falsifies the evidence or falsifies the argument, that involves solving the same kind of problem. These things nicely fit inside of NP. It's a little bit misleading to talk about complexity classes, is we're not talking about Sudoku as played on an n by n grid as n goes to infinity. People play proof Doku at 9 by 9. 9 by 9 is never going to change. So these are all constant size things. If you want your AI system to invent just one valid argument, you need to say there exists an evidence set such that for all completions of the board, none of them disagree with that. So even just finding one valid argument is something tricky that you're not going to get from your run-of-the-mill SAT solver. If you want to do some of the things like find the smallest argument, which we use to, when we populate the board, there's a little par score in the corner that says, you can do this one in 8 moves. Where does that 8 come from? We have to optimize the size of the smallest argument across all these different things. Likewise, getting some of these hints are, I guess, horrendously complex search problems, but were sort of things that ASP could already do, and it was easy to expose these in the game. So last slide, some takeaways. Based on this experience, we're more confident that ASP is ready to face the public in live interaction, particularly with a couple layers of caching in front, so you're not just hitting the solver every single time. Please do stand on the shoulders of giants with both AI technologies like ASP and the zero-cost offerings from cloud services. If you were doing a deep learning project, they have a lot to offer in that area. And finally, this AI-based game design practice gets us new game designs, new AI architectures, and it's actually really fun to do, to see something that previously only ran on your laptop, now run on all sorts of devices without you having to worry about, like, is the server up or not. So that's it. Thank you. Any questions? Okay. Oh, yeah, go ahead.
So in this project you use Sudoku, and I'm personally a big fan of other kinds of Japanese puzzle games. So how do you think that this would be pretty easy to generalize to like other kinds of games in that space, or like, you know, let's say I wanted to get a version of this running for something like Nonograms or Very Common, would it be pretty straightforward? In other research projects, we've already made a similar, not interactive thing, but a Picross or Nonograms puzzle design assistant that as you're painting in the clues, it tells you, are your clues unique, highlights the cells that would make it unique if you if you flip them from black to white or the other way around. So, and at reasonable sized puzzles, we know these solve within a quarter of a second also. In terms of the sort of game design of providing evidence, in Sudoku, it makes sense to click on individual cells. We'd have to iterate to figure out, like, do people click on subsets of the puzzle completed? Do they click on the row and column clues? Like, it takes some translation of that stuff, but I think for many of these logic puzzles with unique solutions, the mechanic of provide sufficient evidence to make a unique argument for a subset of the puzzle could be transferred. And then at that point, it wouldn't be like an AI research project, it would just be pure game design at that point, because we have the infrastructure to just throw at it. Is there a question over here? Okay. Well, thank you.
All right. So now we have our second speaker of the session, and if you'll give me 1 second to get his slides over. And it's Control L. Cool. So here we are.
Hi everybody again. So I'm Vadim Bulitka, and this is my second talk at the workshop. So this is very recent work which just started last summer. So there's probably more here as sort of food for thought as opposed to answers. Okay, so it's about creating interesting characters, AI characters, interesting defined in some way, and that's up for discussion what interesting is. So I want to start with a quote that I used yesterday. So for those of you who were here, it's a repeat. For the new folks joining us today, it's a quote from Stanislav Lem's story, Dr. Diagoras. It's part of this Tichy adventure stories. And here, the protagonist is meeting up with a crazy scientist, Dr. Diagoras, who is commenting on the state of AI. Now, this was written in 1983 in English translation, and so it's at the time the term cybernetics was used. And so the character in the story is arguing that the problem with AI is that the creators require obedience from their creatures, and that's a dead end. So, in fact, he's arguing here that if you had a calculator which would extract square roots from even numbers but doesn't want to do so for odd numbers, that would be a great thing. We should amplify that and should have more of that. So I'm interested in that. So I'm interested in creating creatures which may exhibit some spontaneity, possibly something you would call free will, have their own desires. And 10 years ago, I worked at Institute for Creative Technologies together with Mark Rydell and others. And it was interesting because we actually implemented a bunch of emotional models based on appraisal. And that was great, but it's not something that emerged. It was something done to borrow knowledge from psychology and create NPCs which appear to be emotional. And there's a discussion to be had whether, modeling emotions in the style of OCC or Emma or any other model is really giving those emotions to the NPCs, or are they just going through the appearance and reacting in a certain way to appear so. So there's a bit of a philosophical argument. So what's the problem here? The problem I'm dealing with is to procedurally generate AI agents with a group behavior which is interesting, novel, or surprising. And now all of the three terms I'm using here are vague. And many people, what's surprising to one person may not be to the other, and so on. So I want to have agents which either individually or collectively have their own motivations, emotions, and maybe even something which would call free will. So why would we want to do that, especially in light of Musk's comments and all the hype around it? So I think actually that would help us understand intelligence in some way. It may also help us understand how AI agents, when deployed in a society, may react to things. And here, more relevant to this conference, is we can talk about non-scripted, non-player characters in video games. Now, the way I'm talking about intelligence here is sort of this duck test, right? If it looks like a duck, walks like a duck, it's a duck. Whether you would agree that they're actually truly intelligent or not, that's again a philosophical issue. So these models, agent-based modeling in a lifestyle settings, been around for a long time. In fact, back even before computers were widely available for this kind of job, they were used, in this particular case, this is a NetLogo model of segregation, and they have agents maybe in a housing development who have preferences, who they want to be surrounded by, how similar their neighbors should be. And this was actually used they actually ran this with a checkerboard back in the 70s, and now of course it's much easier to do. Let's see, this, I think maybe this is just a screenshot here. Okay, so there's also obviously AI is coming into our society whether we want it or not. And so things like Musk's own cars, Teslas, which have autopilot in them of some sort, it brings up moral dilemmas. So if a car saves its driver's life but kills 10 pedestrians in the process, should it do it, or should it kill the driver and save 10 pedestrians? There's all these issues which used to be fairly theoretical and now are becoming more and more pragmatic. And of course, we have a lot of procedurally generated content in game. This is a screenshot from No Man's Sky, an ambitious title, which perhaps was misunderstood after the marketing campaign. And so there you have a lot of creatures and planets and other things which are procedurally generated. Now, in my own personal opinion, at the moment, they're not quite as interactive enough to be very interesting, but that could be built upon. and eventually they maybe become very interesting, not just kind of run in circles around you and make funny noises. So what's related work here? There's quite a bit, and I'm probably missing a lot, so if anybody has suggestions, I'll be very happy to hear them. So one of the older piece of related work is a work by David Ackley and Michael Littman, published in '91 in one of the AIIDE conference proceedings. So here they were both at Bell Labs at the time, and they asked the question, in the reinforcement learning setting, where does reward come from? And the answer was, well, reward is genetically encoded in every individual. And so if you have a wrong reward function, which rewards you for hitting your head against the wall, that's fine. You will use that reward function inside reinforcement learning, and during your lifetime, you will probably learn to beat your head against the wall, except you will injure yourself and not reproduce. And so that reward function will probably not spread genetically to others, to your offsprings. So they did this back on a Lisp machine, I think, actually, at the time. And it was great. They discovered a lot of phenomena that emerged, such as shielding, which were known in biology, but that actually manifested themselves, emerged. And I think the key part is there's very little was scripted. A lot of behavior emerged. Now, this, I think, is actually less related to what I want to do. So these are drivators and Forza. Let's see, do I have a video here? Yeah.
That flair for personality extends into the drivatar AI system. The idea is that each race against in single player is modeled after a cloud-based version of a real player's driving habits.
It's a system that succeeds in filling out each 16-card grid with distinct personalities, drivers whose behavior and tendencies you can never take for granted. Their mistakes are far less predictable than the vanilla AI of previous games, making those moments you capitalize on their errors that much more rewarding.
So this was a clip from a GameSpot review of Forza. So Forza is a game where you're constantly connected online, so it collects your driving styles and clusters them in some way, extracts some features and creates these driving avatars or drivatars, and then puts them back in the game if you're playing solo. And that's very interesting work, but that's not quite what I'm after here, because here you're using crowd data to create some behaviors. So I actually want novel behaviors to emerge, not imitate clusters of human players. So there are a lot of other work which seems to be related, but not, again, what I'm trying to do. So for instance, deep learning in StarCraft, which is a lot of recent development there, is optimized, or the goal there is to create a strong StarCraft player. That's, again, it's fascinating work, but not my interest. I'm not interested in defeating humans in games. In fact, I may not even have humans in my games. This is more a life-ish simulation where I'm trying to have emergent behaviors. So our approach here is multi-scale machine learning, and I'll explain what it is. So learning happens in several layers. So one layer is evolutionary reinforcement learning in the style of David Ackley and Michael Littman, where your initial policy and reward function are genetic, and during lifetime an individual will learn giving its reward function, and if it's learning well, and if the reward function is good enough, then it will live to reproduction age, reproduce, and so on. So this is not your standard discrete generation genetic programming, so we don't have explicitly defined fitness function, we don't sort population, we don't take the top and allow them to reproduce. Here you can have a grandfather existing at the same time as grandchild, and so on. What's also interesting is that the other layers, so there is a learning happening at evolutionary layer, learning happening during lifetime, but there is also meta-evolution happening. So the idea is that, because this is all stochastic, on any single run of this evolution, you may not get any interesting behaviors. It may be just boring. And in fact, I would expect most of the time it would be. So what parameters would lead to, what physics of the world would lead to interesting behaviors? I don't know. So the idea is to actually also evolve the world. So if you think of each planet like a No Man's Sky tradition, you have evolution happening within the planet, which I don't think No Man's Sky is doing currently. And then you also have a population of planets, and you're evolving those as well, eventually hoping that you evolve interesting planets. And then the question is, what is interesting and how to detect it? And because I expect that most of the evolution runs will result in non-interesting behavior, I actually need, and I'm not going to sit and watch millions of evolution runs myself, I am actually going to have a machine observing this simulated evolution and detecting, hopefully, things automatically. Now, this is very much a work in progress. Started just in May, so there's some people here on the slide, some of which were in the audience here, who worked with me on it. So I very much welcome suggestions, so whatever I miss in my related work, and so on. Okay, so we decided to start very simple. So we took the predator-prey model. So predators are wolves and prey are rabbits. And this is, we used NetLogo just because it's so simple to start, it's cross-platform, and has this meta-evolution level, evolving the worlds already built in. So I think this is the video here. So visualization is not very exciting from a AAA perspective or even indie perspective. These are just triangles running around in this setting. Orange triangles are rabbits, because our rabbits are orange. And we have also blue wolves, okay? And so we can pause at any time, we can observe, we can click on them, look at their genetic makeup, we can look at their any parameters, so we can inspect any of them, courtesy of NetLogo environment. There's limitations to it, obviously, but I think as a first step, as an interesting test bed. Okay, so I already mentioned some of it. This is asynchronous, no discrete GA generations. No explicit fitness function, just like in David Ackley and Michael Littman case. And what else important here? I already mentioned a bit of that, evolution of the world. So we can do this meta search where the physics parameters are also evolved. And now about detection. How do you know what's interesting? I've been not talking about it yet. And the answer is I don't know what interesting is. So I think this is actually, it's one of those things where one may say, okay, I know it when I see it, but I don't want that. I actually want machine to detect it. So the current thinking is we're going to equate interesting with anomalous, in a sense that we're going to have a lot of uninteresting behavior, which we'll inspect manually at first and say, okay, well, these are uninteresting runs. Rabbits learn to avoid wolves, wolves learn to chase rabbits. It's expected it's not that interesting, right? And then with this data, we will train a deep autoencoder, potentially with some feedback, so recurrent. And then we'll run this autoencoder network on further evolutions. And if it signals saying that it's something different from what I've been trained on, it would be called an anomaly. And at this point, it will pass it to the human. So that may work. We have not done that. The issue is that it doesn't distinguish between positively interesting things and just bugs and glitches. So if the system crashes or generates weird graphical output, the network looking at the individual frames of the simulation say, oh, that's interesting, that's anomalous, I hadn't seen that before. Great, maybe it's just a bug. And so I don't know how to yet train it for interesting anomalies. We don't have an anomaly detector yet, but we did do deep learning on that, because deep learning does everything. I'm trying to make it do my laundry so far unsuccessfully. So what's going on here is there are two snapshots. This is a video game map, I think from StarCraft. This is from Moving AI repository by Nathan Sturtevant. And on the left, you have a sample simulation. So green is grass, blue is wolves, orange triangles are rabbits. So this was a random frame from a simulation with a low mutation rate. So standard deviation of 2 on the genes. The one on the higher mutation rate of 10. The network was trained, and this is the data it's never seen before. And it can actually, just looking at the pixel level, single frame like that, it can fairly reliably tell if it was evolved with a high mutation rate and a low mutation rate. Why? How it does it, we don't know. We try to inspect the layers and visualize them. This is AlexNet doing it. Inside AlexNet, we were unsuccessful. We still don't know what it's looking at. This is your black box nature here. Some reviewers, when they saw this paper, said, well, you know, look, on the right, there's more rabbits, more orange, so maybe it's just looking at orange pixels. Maybe it could be very well be that. So I don't know. But this was just a quick proxy to see if we can even learn anything from or detect anything from a single frame of evolution visualization. So what's the application to games? Well, there's idea of evolving ecosystem in games. It's been around for a long time. Here is an interview with THQ, when they were still around, about Stalker, which was released, what, 2005?
The Holy Grail for FPS in terms of single player is building a believable experience. So rather than having standard box AI that's really predictable, one of the things we're looking for in Stalker is random AI. And it's based on a concept they call an artificial life. And that's an ecosystem that drives the whole life systems around the zone. So the key thing that we're trying to demonstrate is that if you go into the zone and you go to a certain area which is novel, you'll find that a stalker may be there because he's running around shooting some of the animals. If you went to that area again, that stalker may actually have been killed by the animals. So you're getting a random experience. So what we're doing is we've basically mapped out areas of the game that are going to be randomly generated. So that lends itself to a unique gameplay experience every time you play a game.
So that was the intention. This was before the game was released. When the game was actually released, how many people played Stalker? Nobody? Okay, so it's a first-person shooter set in a fictional Chernobyl, and there is supposedly animals, and there are animals. They do about this. So let me. Does that go to the next slide? Does that break? Oh, here you go. So, yeah. So this is what actually end up happening. They just play animations standing over corpses of virtual players which were never there in the first place. And it's fairly disappointing when the game was released. So there were no ecosystem that players could see. They were basically a lot of scripted NPCs and animals occasionally interacting with each other, or at least playing animations interacting with each other. And I think part of the problem is that what makes for an interesting AI project or a live project may not make for an interesting gameplay. Let's say I'm playing Call of Duty and my enemies, instead of attacking me, decided that, we don't feel like attacking you today. We're just going to be friendly. We're only going to stand in the corner and tell jokes to each other, right? Now, from my perspective, that's awesome. That's interesting. I want to see that. If you're playing Call of Duty with a mindset, I want to go shoot things, then maybe it's less interesting. So the less control game developers have, the more interest I have from perspective of evolving AI, but less, potentially the game will not be as interesting. Okay, so there's lots of current shortcomings and therefore future work. We actually currently don't do reinforcement learning during lifetime. We will shortly. We tried deep learning, Q learning, and it works, but we don't have any results on that yet. We don't have any anomaly detection yet. There was a proxy of supervised learning in place. Anomalous is not necessarily positive surprising. It could be something bad, something uninteresting, bugs. How rich should the environment be? Is it enough to have grass, wolves, and rabbits? Do you need something of the level of Dwarf Fortress or somewhere in between? How computationally feasible is this? If we're running evolution at the level of individuals and also evolution of the worlds, it's very computationally expensive. Do such NPCs make for a fun game? And I guess depends what kind of fun in a game you're looking for. And then if we want to use this to argue that it's related to reality, such as animal behavior, there needs to be validation as well. So in summary, my goal is to have novel AI behaviors, especially particularly in groups of agents, because I think a lot of interesting behaviors emerge when agents interact. I want it to be machine learned at 3 different scales: individual, generational, and world scale, and I want it to be automatically detected. I argue that there's interesting applications such as artificial general intelligence, AGI, human-animal psychology, possibly societal issues, and last but definitely not least, non-playable characters in video games. We are looking for collaborators and students on that. The website is AGI untitled-lab.net. Thank you very much. Happy to take questions. Yes?
So you already mentioned this, that novelty and uniqueness is not the same thing as fun. So is the hope that you create this incredibly large world with lots of individually unique things in the hope that the player will eventually stumble across something fun? I mean, how are you going to ensure that people are having a good time and aren't just bored and easily?
Yeah, I don't know. So that's a good question. So part of it, I think, is also player selection. So the players attracted to these kind of games, probably not the players attracted to first-person shooters necessarily, right? So people who play Dwarf Fortress, there's a strong community, but it's not mainstream community, one may argue, right? So part of it is self-selection of the players. Part of it is when we define that function which looks through gazillion evolution runs and detects anomalies, perhaps we can somehow bake the player fun into it, and this is ongoing theme. I myself worked on that on a narrative side. What makes a fun story, a fun narrative? And some of it could be machine learned. That's been shown in the previous work, but we haven't applied it yet. Excellent question. Any other? Jim?
So you asked for pointers to other kinds of work. Reminds me a bit of this community called generative social science, where they've been doing a lot of agent-based modeling, and some of the work you're doing reminds me of this simulation sugarscape.
Okay.
So those are familiar.
Yeah, so I've looked in some of that, but I think we need to definitely look more into it.
Okay.
Yeah, thank you.
So what do you see what you're doing is kind of different than that, or do you think it's similar?
Yeah, so I don't know. So I guess unlike some societal simulations which they want to have validity to, they're restricted by sort of society as an existing society. I have no such restrictions, right? So I'm open to fantastical environments and so on, right? So I'm less concerned with validation at first, at least. So I just want some weird, interesting, novel behaviors. I want calculators which refuse to calculate numbers. Occasionally, maybe on Mondays, but they're okay on Tuesdays with that. Now, I'm not quite sure how to evolve that immediately from this, but that's my eventual goal, is to have the creatures which I would come in the morning and somehow interact with, and they would surprise me. Not in a way, oh, that code broke again, I have to go fix it, but in a way like, wow, maybe in retrospect I can expect it. So let me give a specific example in terms of wolves and rabbits. I don't have it in the slide because we're still looking into it. What happened during summer, we evolved rabbits which did not like grass, but they lived for a long time. So at first we thought it was a glitch, definitely a bug. How can they live for a long time if they don't eat grass? It turned out that they liked following other rabbits. So they had affinity for other rabbits. So population was composed of rabbits which liked grass and the rabbits which were groupie rabbits. They would just follow other guru rabbits around. And this is my names. Obviously they don't call each other this way. And so that's how they survived. They were just in the right. So in this simulation, as long as they're in a grass patch, they automatically eat. So by following the other rabbits which knew what they were doing, these guys would be kept fed and therefore survive. We did not expect it. When we first saw it, we thought it was definitely a bug, but investigation showed no, it's actually a reasonable policy in this environment, given the physics of the world. So these kind of things, I think, are quite interesting. Of course, this is super simple, but if it can be more complex. Yes? Oh.
Okay.
Hi. Sorry?
You were talking about how complex do the worlds have to be, and there's an argument in sort of the evolutionary that evolutionary algorithms themselves are fairly simple, and the complexity of the results come from sort of the complexity of the data they're working from. So there's a maybe valid theoretical argument that the world needs to be pretty complicated if you want to get interesting behaviors.
That's right. So there is that, but also I would mention that in agent-based modeling, a lot of complexity arises from interactions.
Right.
It's not an isolated agent, and this has been done, like Boids, for instance. So everybody familiar with Boids, as beautiful, elegant flocks of simulated birds. The actual rules controlling each Boid are super simple. So Craig Reynolds, when he worked for Sony, when he was doing it, and yet it produces this awesome organic-looking behavior. So I think part of it may emerge here, and that's why I'm emphasizing the population level behavior, or like group behavior. Yeah, you had a question back?
So the groupie rabbits example is really cool, but it's totally useless if the player doesn't have access to those data. So transparency here is also
absolutely. And the talk in the morning, the first talk, I think is very relevant as to how do we reveal. So we inspected it by looking at their genetic composition, something the player perhaps would not do. So if this groupie rabbits can actually express their dislike of grass, right, somehow in a way that player could see easily, that would be awesome. Because then, as a player, you'll be able to see the same phenomena that we as the researchers saw in the summer and got fascinated with. Yeah. Any other questions? Okay, thank you.
All right, so that would be our papers for EXAG. We're off to lunch at this point. At 2 o'clock, we'll be back with some demo presentations. And once again, if you want slides for me to send them to me, and I'll have my computer set up, but after that's done, we will do a quick, brief swap around and get my webcam pointed at the screen or something.
Yeah, so for anybody who is not using slides and demoing off their machine, you'll be going second after everybody who currently has slides on Joe's machine.
Yep.
So we will see you all back here at 2.
Yeah.
And there will be demo presentations followed by interactions with the demos. And
and just generally hanging out until they kick us out because there's dinner in here again.
is that right, everyone?
That's what happened last night.
Well,
Anyway, bye stream.
Bye.